All right, so chapter 5 starts with springs. You're going to have not every problem, but definitely a few of the problems will have springs in it. So you got to know the basics of springs. Now, before we start any of this, I want to point out that chapter 5 problems, the chapter we're just beginning, many of the problems look remarkably similar to what you just did in chapter 4. So that means, as you crack open the book and you start the chapter 5 homework, you have to fight the temptation to solve the question using your chapter 4 skills, right? You want to try to use your new knowledge, which is the chapter 5 stuff. So basically, it's the same sort of problem that you're going to be solving a different way. So why do you have to be able to do it two different ways? I'm going to tell you why. Because on the AP test, the College Board will say, hey, here's the problem, solve it with forces. Or they'll say, hey, here's the problem, solve it with work and energy. On the free response, they're going to tell you how they want you to do it. So the problems are very similar, but you want to, since we're in chapter 5, solve it chapter 5 style. On the quiz, which is multiple choice, you can do it however you want. But I think I'm going to set the problems up so you're going to be forced to do it chapter 5 style. All right, so the basics of springs. First thing to know about springs is this equation here, which is referred to as Hooke's law. Hooke's law is the equation for the force of a spring. And it says that the force of a spring equals negative kx. Well, what's k? K is what we call the spring constant. And every spring has its own constant. Okay? Every single spring has its own constant. So if you take the spring constant of a spring and multiply by the displacement of the spring, which is simply how far the spring was stretched or compressed, that's going to give you the force. So let me make this really super duper clear. So say I take this spring right here, and I'm going to give you the spring constant. Let's say that this spring has a spring constant of 100 newtons per meter. If I grab that spring and I stretch it 1 meter, would that spring be giving me a force? Yes. In fact, what would the force of the spring be? If you knew that the spring constant was 100 newtons per meter and you stretch the spring 1 meter, what would be the force of the spring? 100 newtons. And which way would the force be? So I pulled the spring to the right. So in physics, our sign convention, to the right is plus, to the left is minus. Okay? So this 1 meter right here, that's the delta x, and it's plus. Why is it plus? Because we went to the right. Which way would the force of the spring be? To the left. The force of the spring would be to the left. And what would it be? 100 newtons, right? Now, why negative? Because it points to the left. So in this equation here, this negative force of spring equals negative kx. All that negative is saying is that the force of the spring will always be opposite the delta x. If you pull a spring to the right, the force of the spring will be to the left. If you pull a spring to the left or push a spring to the left, the force will be to the right. Force is always opposite displacement. Does that make sense? So what if I pulled the spring 2 meters? What if I changed this 1 meter? What if I changed it to 2 meters? Then what would happen to the force? It'd be 200 newtons. So if you're a little bit confused, the logic we're using here, like if you make $100 an hour, which would be incredible, if you make $100 an hour and work for 1 hour, how much money did you make? $100. How about if you make $100 an hour and you work for 2 hours? $200. It's the exact same logic. It's force per meter. Okay? I guarantee you're going to come across a problem where you're going to be given a graph for a spring being stretched, like this right here. So this is the graph you would get if you plotted force versus displacement. So it's kind of like Here we're stretching, 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 farther, farther, farther. We're pulling the spring farther, 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 farther. What happens to force as you pull a spring? As the spring gets stretched, what happens to the force? The force goes up, and it's linear. If it's an ideal spring, which it will be, it's going to be a nice, perfect, ideal spring. As you pull the spring, the force goes up. All right. On a graph like this for a spring, there is one, actually two, but for right now I want to focus on one. There is one thing for now that I want you to know, and that is slope. What would the slope of that line be? Well, let's figure it out. Slope is rise over run. So, it's a straight line, so we'll use 2 points, okay? We'll use 2 points. What is the rise of this line? The rise is the what? It's the force. It's the force of the spring. What is the run? The delta x. That's the displacement. Force of spring over displacement. Look at Hooke's law right here. Here's Hooke's law. Solve Hooke's law for K. What is K? It's force of spring over displacement. So what is the slope if you're given a graph of force versus distance stretched? What's the slope going to be? It's the spring constant. Do you guys follow that? It comes out in newtons per meter. It's force per stretch. Okay. Lots of today and tomorrow, dude. Lots of lecture. Okay, this next screen here. So the key thing I'm focusing in here is I want you guys to have the idea of equilibrium position. You're already familiar with the word equilibrium from last chapter. Let's just review what that means. What does the word equilibrium mean? Equilibrium means, who remembers?
Net force is zero.
Net force is zero, or acceleration is zero. Nice. So remember last chapter, this was the main equation. F net equals ma, right? Well, if an object is in equilibrium, you could either say that means the net force is zero, but if the net force is zero, what else is zero? The acceleration, right? So equilibrium means no net force and no acceleration. So this applies to springs here. So I want you to look at this situation. So here's a situation. We have a mass that's been attached to a spring, and this mass is going doing, 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 doing. It's bouncing up and down, right? The equilibrium position, which I'll explain, the equilibrium position is this line right in the middle. So when the ball on the spring is right at that line, that is the equilibrium position. And what do we mean by equilibrium position? We mean no net force, no acceleration. So when the ball is here, right, what's the acceleration when it's at this level here? The acceleration is what? 0. How about when the ball is down here, at the lowest, but down there? What's the acceleration at the bottom?
0.
Not 0. Maximum. How about when the ball is at the highest point up here? Maximum. Right? So the top and bottom have maximum accelerations. At the equilibrium, the acceleration is 0. How about velocities? What's the velocity at the highest point up here? What's the velocity up there? 0. What's the velocity at the equilibrium? Right here in the middle, what's the velocity? Maximum. What's the velocity at the lowest point? 0. So it's kind of like, here's the equilibrium. Acceleration is 0. Here's the highest point. Here's the lowest point. Okay? Now, why is the middle the equilibrium? Because when the ball passes through the equilibrium, let's look at the forces on it. when the ball is right here, what are the forces on the ball? Well, we have mg down, and then what's acting up? The force of the spring. At the equilibrium position, those two forces are equal for a split second. For a split second, those two forces cancel. So if those two forces cancel, what's the net force? Zero. And then what's the acceleration? Zero. Okay, now let's look at the lowest point. At the lowest point, we have mg down, force of spring up. Which force is bigger here at the lowest point? The force of the spring is bigger, and how do I know it's bigger? Because what's going to happen a split second later? It's going to accelerate up, right? So the force of the spring is bigger than mg. Okay? At the very highest point, what's the force there? There's only one. mg. There's no force of spring up there. Why is there no force of spring? Because the spring is totally what? Limp. It's totally like a spaghetti noodle. It's loose. Okay? So, all right. Equilibrium is where acceleration is zero. Oh, and look. What do you call the maximum distance from the equilibrium? You learned this in chemistry. What is this A right here? Have you guys heard of the word amplitude? Amplitude. So if you don't know the word amplitude, make note of it. Amplitude is what? It's the maximum distance from the equilibrium. And in chemistry, look, in chemistry you guys talked about waves. We'll talk about waves in this class. Look at, there's some tasty waves. Sweet Spaldo. Look at surfing that. Woo! Catch it. No fun. So look, where's the equilibrium position for a wave? Remember this from chemistry? The equilibrium position is where? Right down the middle. If the wave died, where is it going to die to? The middle. Hey, when this mass on the spring stops going up and down, where is it going to die to? The middle, the equilibrium. So for a wave, here, there's the amplitude. It's the maximum distance from the equilibrium. There's the amplitude. Amplitude is maximum distance from the equilibrium. Okay, let's keep moving. So lecture 2 right here. Okay, work and energy. So now we're getting to the good stuff here. In fact, if you look in the textbook or the Spaldo notes, what's the title of chapter 5?
Work and energy.
Work and energy. So the first thing to know about work and energy is they both have the same unit. They both have the same unit. What do we measure work and energy in? The joule, which is abbreviated with a capital J. Now, a joule, just like the Newton, it's a much bigger unit than just what we write. Joule is a shortcut unit. What is a joule in its entirety, in its full form? 1 joule is equivalent to 1 kilogram meter squared over second squared, which you have to know this. But look, there's an easy way. You can always figure it out. You don't have to necessarily like hardcore memorize it, because you could figure it out from any equation that's work or energy. So for example, here we have the basic equation for work. The fundamental basic equation for work is force times displacement. So what is force from last chapter? Newton. And remember, a Newton is actually a bigger unit. Okay, what do we measure displacement in? Meter. So you could say, so work is joule. Work is going to be joules. So you could say that a joule is a Newton times a meter. Sometimes a joule is called that, Newton meter. But what is a Newton? A Newton is a kilogram meter per second squared. right? So that's what a newton is, and then times a meter. What does that give us? That gives us a joule. Now, dude, let's say you forgot what a newton was. I just want to review with you. Let's say you forgot what a newton was. How could you figure out what a newton was? F equals ma. So you're like, oh yeah, force is newton, m is kilogram, a is meter per second squared. Oh yeah, that's a newton. Kilogram meter per second squared. Does that make sense? Okay, so the thing to know about the basic equation. Oh, I forgot one part, by the way, too. Look, I want you to know that the definition for energy, because work and energy are both in joules. If you look up the definition for energy, it's going to say energy is the ability to do work. Energy is the ability to do work. If you have zero energy, can you do work? Nope. That's why you eat food, right? To keep, so then you can like walk around and do work and lift things and like, move your pencil. That's all work. So watch me. I'm going to push on this lab table as hard as I can. Ready? And if I blow my back out here, it was worth it. Okay. So I'm going to push on this table. Ready? Did I use energy? Yeah. Did I do work? No. Why did I not do work here? Because if you look at the definition for work, it's force times what? Displacement. If the object involved does not move, how much work is done? Zero. No work is done unless something moves. Okay? Although, what you just witnessed was me using energy, but failing to do work, because I didn't move it. Okay? In this equation, you have to know that force and displacement, these two must be parallel. F and delta x must be parallel. That's like huge. So for example, here on the left, this would be the easiest possible situation. What makes this situation really nice? Well, the force and the displacement are parallel. So if you wanted to find the work done by that force, all you'd have to do is multiply the force by the displacement, and your money. You got it done. Now look at this situation here on the right. This situation here, it's a little bit harder, because what do you notice about this applied force? So this force right there, is that force parallel to the displacement? No. So what two things are going to get multiplied here? What you're going to have to do is use the x component, right? You're going to multiply the x component by the displacement. Now what if we started talking about normal force? Sure. What if we throw in the normal force here? So this block is on a surface, so it's got a normal force. Fn points up. Is the normal force doing any work? No. Hey, is mg doing any work? So mg points straight down. No. And the way to just wrap your brain around that, is which way is the motion? The motion is this way, right? Can the normal force get in there and like affect the motion? If the motion is perfectly in the x and the normal force is in the y, can the normal force butt its head in there and be like, hey, well, what about me? Nuh-uh. It's perpendicular to the motion. So forces that are perpendicular to the motion, how much work do they do? Zero. All right. So, dude, I'm going to give you guys a little problem here. It'll kind of break up this long lecture. And, okay, so we got this gold bar, kind of random. I like to have gold bars around, like at my house when I do physics stuff in the garage. I like to use gold. It makes whatever I'm doing feel important. Okay, so I got this 5 kilogram gold bar that I keep at my garage, and I like to pull it, drag it across the floor, and figure out how much work is done. So the question is, if the pull force this force that's pulling the bar is 20 newtons. This angle here is 35 degrees. The force of friction is 7 newtons. You're going to find the work done by the 4 forces on the bar. How much work does the pull force do? How much work does friction do? How much work does normal force do? How much work does gravity do? So very easy question, just, we're early in the chapter. So I'll give you guys 5 minutes. Answers. So the first question, what's the work done by this pull force here? And the displacement of the gold bar is 15 meters. Now, to find the work done by the pull force, can we just go 20 newtons times the 15? No, because they're not parallel. The key thing, if you remember nothing else from today, although it's hard to choose what to remember and what not to, but I would say high up on the list, you have to know that in the work equation, work equals force times displacement. These guys have to be parallel. So to get them parallel, we have to do some trig. What did I do here? There we go. So this is 15 meters. So we're going to have to do some trig. We need to get the x component of the 20. So we're going to go work equals cosine 35 times 20, then times the 15 meters. So what's cosine 35 times 20? That's the x component of the 20 Newton force. And the x component of the 20 Newton force is parallel to the 15 meters. So this comes out as 245. I lost my paper. I think it comes out as like about 245.7 joules. Now, the sign convention for work, okay, it's very easy. And it's in the Spaldo notes if you forget. The sign convention for work, if a force is doing work in the direction of motion, that's considered plus. That's considered positive work. If a force is doing work against the motion, that's considered minus. So look at our 20 Newton pull force. Is this force here acting in the direction of motion or against the motion? With the motion. So this is positive work. All right? So that's the answer to number 1. Okay, number 2, friction. Now what's really nice about friction? Friction is parallel to the displacement. Is it going to be with the motion or against the motion? It's against the motion. So we know that the work of friction is going to be negative because it's opposite motion. So then all you do is you go force, 7 newtons, times the displacement, times 15. So this comes out as negative 145. So negative because it's opposite motion. Okay? Oh, 105? I lost my notes. Oh, that's right. This is 105. Okay, 105. Okay. Hey, something else is 140, which I'm going to get to. Okay, number 3. What's the work done by the normal force? So look at normal force. Is it parallel to the motion? No. Does it have a component parallel to the motion? No. So how much work is the normal force doing? 0. How much work is mg doing? 0, because it's perpendicular to the motion. Okay? Now remember I said that chapter 4 and chapter 5 are very similar in a lot of ways. So here's one connection I want to make. What is the net work for this problem? So how many forces were doing work in this situation? 2 forces were doing work. The pull force does work and friction does work. What's the net work? Well, the net work would be these 2 added together, right? Which would come out to be positive 140, around there. The net work is positive 140. If you have net work, that's telling you something. If net work is being done, what must be happening to the object? Not just moving, it's accelerating. And let me show you why. So here we go. Work net. So what's the basic work equation? F times delta x. But if you're talking about net work, which is simply total work, then this F is F net. Work net would be F net times displacement. But wait a minute. What's F net? From last chapter, what was F net? That's MA, right? F net is MA. So here's the idea. If you have net work, there's going to be an acceleration. The object will be accelerating, right? If you have net, in fact, let me put it this way. If you have net work, that means you have a net force. If you have a net force, you have an acceleration. So it's very similar to chapter 4. You're just doing it a different way. Okay? All right, final thing for this period, and then we're done. So let's see, now we're on to part 3. Okay, work and energy basics. Okay, there's 3 forms of mechanical energy. Now, what is mechanical energy? Mechanical energy is useful energy. We're just going to, that's my simple definition for mechanical energy. It is useful energy, although that's kind of a weak definition. I don't know, but I think the official physics definition is it's kinetic energy plus potential energy. But mechanical energy, there's 3 forms of it. And you've all heard of the first one. You've all heard of kinetic energy. What is kinetic energy? The energy of motion. How do you know if an object has kinetic energy? If it's moving. Like, does this brick have kinetic energy? No, because it's not moving. It's sitting there at rest. 0 kinetic energy. And remember, what unit will all of these be in? These will all come out in what? Joules. So look, if you were trying to figure out what a joule was, you could use any of them. Like, let's use the first one. So what is mass? Mass is what? Kilograms. What's velocity? Meter per second. Oops. Hold on. So that's meter per second. But then you got to square everything. So then that gives kilogram meter squared over second squared, which is what we said a joule was, right? Okay, so all of these are measured in joules. Kinetic energy is the energy of motion. Now, what do we mean by potential energy? So notice here we have potential energy due to gravity, and we have potential energy due to a spring or something elastic, like a rubber band. What does potential energy mean? It's simply, anybody know a definition for potential energy? Stored energy. It's energy that's been stored. So can gravity store energy? Yeah. And let me give you an example. So see this girl here holding this ball? Now, I like to explain energy, especially for gravitational potential energy, because kids oftentimes have a hard time wrapping their brain around gravitational potential energy. Look, if you were to lay at the bottom of this cliff, if you laid down at the bottom of the cliff here, looking up, and this girl dropped that ball onto your face, would that hurt? Yeah. In order to feel some sort of pain, there had to have been some energy there. You can't hurt yourself without energy, as awful as that may sound. But look, if she dropped that ball onto your face, you would feel the potential energy that was stored up there. You know? Like, see this brick right here? So it's Eric, right?
Yeah.
So look. So this brick, I hold this brick up like this. Does this brick have energy? Yeah. If I let the brick go and it crashes onto Eric's head, Eric would get a good feel of how much energy there was, up there. So an object, due to its location, can have what we call potential energy. But to make this even more clear, look, The thing we got to talk about is this H. This H right here is the definition of H is it's the vertical height, and this is typed up for you in the Spaldo notes. It's the vertical height above or below the 0 point. Now, what is the 0 point? The 0 point is where we measure H from. So look, does this ball here have potential energy? Yes. Now somebody say no. No. Okay, you're both right. You could argue that this ball has potential energy, or you could argue that it doesn't have potential energy, because whether or not it has potential energy depends upon where the 0 point is. So if you put the 0 point right here, if you say that that's the 0 point, then what's H? Then H is 0, and guess what? The ball has no potential energy. If you say that down here is the 0 point, then guess what? The ball has potential energy. Now the question becomes, where do you put the 0 point? And the actual answer is, you can put the 0 point wherever you want. You could put it wherever you want. Like you could stick it right here in the middle. But I wouldn't recommend doing that because look, if an object passes below the 0 point, so say that you make this the 0 point up here. If that's your 0 point and she drops the ball, now what are you dealing with? You're now dealing with negative potential energy, which is a bummer. You don't want to have negative potential energy. I mean, it's doable, but it just makes it harder. My advice to you is put the 0 point at the lowest point in the problem. So you're going to be given a problem that involves potential energy. Identify the point that is the lowest and make that your 0 point. And that's where you measure H from. Does that make sense? Okay. Okay, spring or elastic potential energy. Can you have energy in a spring? Yeah, like look, toy guns. How do toy guns work? So here we have, what's inside a toy gun? A spring. What happens when you smush the spring? Energy gets stored, right? It's stored energy. How do you find the energy in a spring? With this equation. What's K? The spring constant. What's X? How far you smush the spring, right? So we got 3 forms of mechanical energy. We're going to end here for today. Any questions on this? Okay, so tomorrow, do we have like 2 more days of lecture just to get this chapter started?